Now that we've got the limit laws, let's put them to work. Let's give a few examples for why we like them, why we use them. If you think about it, there's not that many limits that we can calculate straight from the definition. Most of the tools we have at our disposal, it would be if you've got a function, you have to graph it and just sort of look at what the graph does and estimate it. For certain very basic functions, we know exactly what's going to happen. So like if I took f of x equals x, then you know that the limit as x goes to a could be any number, 3, 4, 5, pi, -1, 10 trillion. Limit as x goes to a of f of x, that's going to be limit x goes to a of x, which is just going to be equal to a, because the y value is equal to the x value. As the x value goes to a, the y value goes to a as well. So we can leverage this using the limit laws to do lots of other things. So say that I had a new function. So let's set that example aside, and let's say now we make a new function, still call it f, and say that it's just some polynomial. Let's start with a quadratic polynomial, maybe 2 times x squared plus x minus 4. And say you want to take the limit. So here's a homework exercise. So say you want to take the limit as x goes to, I don't know, x goes to -1 of f of x. And I'll just rewrite it. So you want to find out what this limit is. Intuitively, what's going to happen is just plug in the number, plug in -1, and then that'll be the answer. But why does that work? In a typical calculus class, you'll see problems like use the limit laws to figure out such and such limit. So let's see how to break this down using the limit laws and find the answer. So the only thing that we've got at our disposal are basically the product rule, the sum rule, and that constant multiple rule. So I just look for two things that are added together, like 2x squared plus x minus 4. So the sum rule is telling me that this is going to be limit as x goes to -1 of 2x squared plus limit as x goes to -1 x minus 4, right? So I used the sum rule to break this up into two component parts that are a little smaller. So next step, I want to use the constant multiple rule. So here I'm taking k equals 2 in the constant multiple rule, and I'm saying this limit is going to be equal to 2 times. So I'm following the equal sign from here all the way to where I'm eventually going to end up. So this is going to be equal to 2 times the limit. So x goes to -1 of x squared. And now here I can break this up even further because, well, I want to use this sum rule for limits. And you might say, well, Ken, you can't use the sum rule for limits because that's not a sum. Or is it? Because what I can do, if you like, you can think of x minus 4 as x plus -4. That might seem a little strange, it's a little funny, but it's legitimate, it's valid. So the limit of x plus 4, in other words, the limit of x minus 4, using that sum law is going to be limit of x minus limit of 4. So I'll just write that down here. So this is limit x goes to -1 of x minus, plus the limit x goes to -1 of -4. And now we're almost ready to start calculating things. Well, the only thing that, strictly speaking, I don't know yet is this one. What's the limit of x squared? But here I can use the product rule that says the x squared is x times itself, or I can use that exponent rule I showed you earlier. In fact, the limit of x squared is equal to the limit as x goes to minus 1 of x and then squared. That's what that exponent rule said, right? The limit of the function squared is equal to the limit of the function and then square that quantity. So I've used that exponent rule, I've used that product rule. And you add the rest to it. And now you can really start calculating everything, because I know that the limit of x as x goes to minus 1, that's definitely equal to minus 1. That was the first remark that we made. Here I'm taking a equals negative 1. And so I'm going to get 2 times negative 1 squared plus negative 1. Or you could write that as just minus 1 if you wanted to, but either way, plus negative 4. Let's calculate that out. So negative 1 squared is 1, so I get 2 minus 1 minus 4. And so that's 2 minus 1 is 1. 1 minus 4 is going to be negative 3. So the answer is negative 3. And you see what happened is, at the end, this is really the same thing as plugging negative 1 into this function. You can see me substituting negative 1 for x. Here it is. So you might say, why can't I just immediately skip to the end and plug in negative 1? And the answer is, you can. I won't stop you. But as we're first learning this, what you're going to want to focus on is the fact that the reason why you can is because of those limit laws. So that's sort of how mathematics works. You build things up step by step, and then once you've got that scaffolding, once you know how to do it, then you can just skip to the end and get the answer. So let me show you one more application of the limit laws that I really like. That's not quite so easy. Actually, I shouldn't say that this is easy or hard. I don't like to make judgment calls. It just is what it is. But let's look at something like, let's make a new function. Let's call it h of x. Let's make this cosine of x times sine of x over x. And I'm going to ask you now, what's the limit of this function as x goes to 0? So what's the limit of this function? And the first thing you're going to want to try, or the first thing that I would want to try, is just to see, can I plug in x equals 0 into this function and get it to work? And if you do that, then you get cosine of 0 equals 1, sine of 0 equals 0, so that's 0 times 1 equals 0 on the numerator. And then on the denominator, you're just going to get x equals 0. So the answer you're going to get, if you just try to plug things in, is 0 over 0. So that's not what you want to write down as your answer. That's what we call an indeterminate form. Or in other words, when we were talking about that limit law, and we said, you know, the limit of the quotient is going to be the quotient of the limits if you know that the denominator, that limit, is not 0. That didn't happen here. So that quotient limit law did not apply. You can't just plug in 0 and hope that it'll work. That also doesn't mean that the limit doesn't exist. The limit might exist or it might not. You just don't have the information by trying to plug it in. So generally speaking, your next recourse might be to try to graph this with some software and just see what it's doing. But actually, since we've already talked about some trigonometry earlier in the class, we're in a position to solve this right now, beyond the shadow of a doubt. And let me show you how to do it. It all depends on how you want to group this function. And the way that I want to group it is I want to rewrite this as cosine of x times sine of x over x. So I'm going to have two functions now. This is my function f. This is my function g. And that product limit law is going to say that the limit of h, the limit of f times g, is equal to limit of f times limit of g if you know that both these limits exist. And so the question is, does this limit exist? And the answer is yeah. So we did that with this thing where we compared the area of two triangles and a pizza slice in between them. We did this inequality that said cosine of x is less than sine x over x is less than 1, provided that x is between 0 and pi over 2. A similar argument will handle the case that x is between negative pi over 2 and 0. So that tells us that it really is true that limit as x goes to 0 of sine x over x is equal to 1. This is like a fundamental important limit. And cosine of x, that's no problem. Cosine is what we call a continuous function. So you can sort of see this by graphing it, or you can believe me for now, but I can explain more later. But the limit as x goes to 0 of cosine of x, that's just going to be equal to cosine of 0, that's going to be equal to 1. So finally, when I calculate the limit, x goes to 0 of f times g, the limit law that actually works, not the quotient law, the product law, tells me this is going to be limit x goes to 0 cosine of x times limit as x goes to 0 of sine x over x. And since I know that this one is equal to 1, and this one is equal to 1, the answer has to be nothing but 1 times 1 equals 1. So this is an example of a limit that to me was not obvious at all at first glance. But using our hard work to prove that this limit was equal to 1, and using the fact that we know the product limit law, we were able to calculate this. And it's also a great example of why that quotient law, of why you actually need the hypotheses or the assumptions for the limit laws, because the quotient rule doesn't work here because you've got 0 in the denominator. Nevertheless, you still can figure out the limit, even though it's not completely obvious. It's true that this limit as x goes to 0 is still going to be equal to 1. So that's one of my favorite examples, early examples of the limit laws.